Yeah, nice to be here. So I'm going to talk about astrophysical probes of the dark sector, and hopefully this short talk is going to be an introduction to both answering some of the questions that Adrian posed and also things we can discuss in the discussion session about how to take dark sector models and turn them into predictions that we can then measure in local Milky Way data or local astrophysical data, such as streams. And so I'm going to be specifically concentrating on the nightmare scenario that Diego talked about, the scenario where the dark sector and the standard model are coupled only very weakly, and our only chance of measuring things are through gravity. And so the idea of this talk is going to be mapping dark sector microphysics onto measurable things in local astrophysics. And so the idea is going to be that if there is some process in the dark sector, imagine you have a dark sector that has self-interacting diagram like this with some mediator that's light enough for this to be important, you can create efficient things like heat flow in a dark matter halo. Or if you have a light particle that can be dissipated with couplings that are large enough for that process to be important, so a dissipative sector, you can have efficient cooling in a dark matter halo. And so the idea is that if you can map between, the particle physics properties, things like couplings, masses, and so forth, onto gravitational effects that then can be measured, you can compare the gravitational effects to data and then say fundamental things about the dark sector that created those effects. So the idea is going to be, how can we create this map between, couplings and masses onto, let's say, the statistics of gaps in streams in the Milky Way, for example. So, of course, one way is to run simulations, and that's obviously the best you can do because it captures all of the nonlinear effects, it captures all of the complicated physics. However, there's issues. One of the important issues is that it's expensive, right? Even in CDM, it's expensive, but imagine you have a dark sector with 3 free parameters and you want to scan over all combinations of those free parameters. You very rapidly run into issues that just make it computationally unfeasible to do that. There's numerical issues as well. You have things like numerical disruption of subhalos, and you don't always know if the disruption is a numerical issue or if it's something else. There's also issues with having the simulations calibrated to the unusual physics that comes about with a dark sector model. For example, if you have very dense objects, sometimes simulations don't capture the correct even gravitational behavior just because of numerical issues. And then, of course, there's issues with finite resolution. You don't really get to resolve down to the small objects you might be interested in. And so what I'm going to talk about today is a combination of using kinetic theory and this idea of semi-analytical modeling to try and make predictions that then you can hone in onto the relevant parameter space of your model of interest and go and simulate carefully and then make sure that the predictions you claim are true are in fact also seen in simulations. But the idea is going to be to use something much more fast that gives a lot of intuition and then find the region of parameter space that is either ruled out or potentially ruled in. So let's talk about kinetic theory. And the basic idea is to ask, is there a fluid description of the dark sector that I care about? So namely, can I write down a set of variables, things like density, temperature, pressure, heat flow, and bulk velocity, and then find a set of equations that can be used to solve for these fluid descriptors? So, of course, one thing that we can do is write down an equation of state. You can imagine that a dark sector that I care about is well modeled, let's say, by an ideal gas. So that's one equation that relates pressure, density, and temperature. And then you can start writing down moments of the Boltzmann equation. Okay? So you can write down the Boltzmann equation, and A here is just a parameter that needs to be powers of the velocity. And each power that you plug in is a different moment of the Boltzmann equation. So if you put down A equals just unity, A equals 1, what you get from this equation is the continuity equation. If you put in A equals the velocity, what you get is the momentum conservation equation. If you write down A equals V squared, you get energy conservation. And in typical scenarios, let's say cold dark matter, if you ask, does the series truncate at any order, the answer is not necessarily. Each equation has in it parameters that depend on the next equation. And in order to solve, you need to go to infinite moments of the Boltzmann equation. And that, in principle, is a problem. And in fact, in CDM, that becomes true, and that's one of the reasons we have to run simulations for cold dark matter. However, in some cases that we call fluids, there's a truncation scheme. There's some scheme that truncates your Boltzmann series at finite order. And for example, one example is the Fourier, the Fourier equation, which tells you that heat flow is related to the gradient of the temperature field through some parameter kappa. And if that's true, you get to truncate your Boltzmann series at finite order, and you get a finite set of equations for a finite set of parameters. So when does this work? One of the requirements for this to work, and Libby mentioned this the other day, is that the mean free path of your interactions be substantially less than typical variations of the temperature in your fluid. So the mean free path needs to be smaller than T over gradient of T. And in that case, that kappa parameter that I talked about goes like the mean free path multiplied by the velocity. So let's just consider a typical test case like self-interacting dark matter that we all kind of know and love, and ask, is this a true statement for cross-sections that we've typically seen in the literature? And it turns out actually that the answer is no. So it seems as if we might be screwed. However, a trick happens because these particles are orbiting in a potential. And that potential typically has high densities at the center, and so all of the action is happening close to the center of the halo. And so you imagine a dark matter particle that orbits a number of times, it has a long mean free path, and then it scatters with some other dark matter particle in the halo, changes its orbit, against, orbits for many, many orbits, and so the mean free path is large. And so then you scatter again, and even though the mean free path is large, the linear distance between scattering events is in fact much smaller. And it's typically about the size of your halo, or let's say the Jeans length. And so because of that, even though the mean free path is large, the distance between scatterings is small. And so what you get to do is you get to exchange this kappa, the mean free path, you get to exchange it with the Jeans length. And the typical velocity in your system, instead of it being the actual velocity, you get to exchange it by the Jeans length divided by the timescale for scattering. So at the end of the day, you get, things that have to do with the halo itself over here, and the cross-section goes only into the timescale down there. And this trick turns out to work, and you actually get to use this to truncate your Boltzmann series, and I'll show you in a minute how these calculations actually match simulations. So let's just take a toy model, and I'll show you how these, a simple toy model, pans out in this language. So imagine you have a model with a chi particle that's your dark matter, some massive mediator phi, and some self-coupling alpha. If alpha is small or m phi is large enough, all of the collisional things in your theory don't really matter, and you end up with a effectively collisionless and cold dark matter theory. If alpha is large or m phi is small enough, maybe this diagram becomes important, and you can call this a self-interacting theory because the cross-section is large enough for scatterings to be important over the age of the object you're interested in. And if alpha is large and m phi is small, and it's such that you can remove this phi particle from your system, you can radiate it away, this might be a self-interacting and dissipative system. And so there'll be some scattering cross-section associated with this diagram. There might be some rate of dissipation associated with the diagram on the right. These things might be, have non-trivial dependencies on temperature and things like that. But you can write them down and calculate them, maybe analytically. And then you can write down the moments of the Boltzmann equation. Okay? So you can write down an equation of state, and then you can write down the continuity equation, the momentum conservation equation, the energy equation, and a truncation scheme. Okay? So what's happening here? This is kappa. This is exactly what you get by doing this trick that I told you before. You get to use the Jeans length as your typical length scale and the time scale for scattering, which is secretly in here. And the self-interactions show up in the normalization of the time scale that I've used for writing down these equations. So inside each of these T tildes, there's a secret cross-section in there. And the luminosity, which is really just the heat flow, is also normalized to a typical time scale, which has inside it the cross-section. So SIDM is sitting inside of these equations with some cross-section that can be varied. And dissipation is just a term that you get to add to the energy equation, right? Because energy can be removed from the system. So you don't need to think about what these equations mean, like you don't have to look at the details, but just to give you a feel that you can now map these particle things like alpha and m phi and m chi onto a set of equations that can be solved and used for making predictions. Okay, and a nice paper by Reuven and company from 2019 did this for a dissipative sector. And what I'm plotting here, or what they plotted here, is the evolution of an initially NFW profile as a function of radius and time with two different values of this dissipation rate. The red is for a high dissipation rate. The blue is for no cooling, no dissipation rate. And what you see, if you look just at the density at the center as a function of time, you see that when there's no dissipation, you initially produce a core, and then you eventually gravithermally core collapse and get this extreme high central density. And when dissipation is important, that same thing happens, except it happens much, much faster. And so you can already imagine how these types of objects, which collapse within the age of the universe, could, for example, puncture holes in GD1. Okay. Other things that you can do with this same type of formalism is incorporate environmental effects, things like tidal stripping, or things like dark ram pressure. So tidal stripping, Adrian mentioned this. This is just the idea that there's some tidal radius where particles that are on the edge of some satellite orbiting within a Milky Way, let's say, are no longer bound or are momentarily not bound to that satellite, and they can be ejected and removed from the system. And dark ram pressure is this idea that if you have self-scattering, you can have scattering events between particles that are bound to a satellite orbiting in some larger object and particles that belong to the host. And as those interactions happen, you can ask the question, for a given scattering event, what is the probability that post-scattering, both of those particles have velocities larger than the escape velocity? That calculation turns out to be analytical, and there is some evaporation rate. So as a satellite orbits through its host, it just loses mass efficiently from its center, and that is proportional to this scattering cross-section for scatters that have velocities large enough to escape at the end of the scattering. And that can be incorporated by adding an evaporation rate into the continuity equation. And tidal stripping can be added also by adding additional function to the continuity equation. And so you can see how you could map all sorts of things of interest onto a very simple kind of model that has spherical symmetry, but can give a lot of intuition as to what you would expect or the region of parameter space that you care about for a given dark sector model. So this is a result by Menage and Company from 2020, where they tried to do this with tidal stripping, and they basically ran this set of equations and tidally stripped, removed mass from the initial conditions of their profile, and asked, what does the density look like as a function of time? And so as you strip more and more, what you find is that the time scale for gravithermal core collapse becomes much shorter. So removing more mass from the outskirts makes it easier to thermalize the central region of your profile and decreases the time scale for core collapse. This is the same result, but this is something that we're writing right now. And so I'm just going to show you here density as a function of radius and central density as a function of time for two different models, an initially NFW profile, and here an initially truncated NFW profile. And you see the exact same thing, that the time scale for core collapse when you initially truncate is a lot shorter than for the case of a non-truncated profile. But here we've also compared the result to simulations, and you can see the blue dots here are the simulations, whereas the yellow is this numerical code, and you see that they match really well. So this does a really good job at predicting what you would have gotten from expensive simulations. And in another work in progress with Frank, we were able to also solve these equations for the case of a constant evaporation rate. And here you see the central density as a function of time for increasing values of this evaporation rate. And you see that as you increase the evaporation rate, the time scale for core collapse actually increases, and eventually you have an evaporation rate so large that you never get to core collapse. So just to show you what that looks like is in density as a function of radius. For this green curve, you have an initially NFW profile, the dashed curve. You core initially, and then slowly you core collapse and the density increases, but it happens much more slowly than if there was no evaporation. And for this red curve over here, you start off with an NFW profile, you core, and then you just lose mass and lose mass and lose mass, and you never get to have a central density that is very large at all. In fact, you probably kill an object that looks like this. You can do the same thing for a combination of tidal stripping and evaporation. If you do this, you find that there are three regions with different types of behavior. A region where tidal stripping is important, but evaporation is not so important, and in that region, collapse happens very rapidly. A region where tidal stripping is not so important, and there collapse happens, but it happens much slower than it would had there been no evaporation. And a region with very high evaporation rates, imagine satellites that have very small pericenters and very small escape velocities, for which collapse is just never possible. Okay? So you can imagine how this kind of mapping can be used to then ask questions about, poking holes in GD1, for example. Okay, other things can also be included in this kind of formalism, things like internal degrees of freedom. You can imagine you have a dark matter, a dark sector that has, let's say, two states, a ground state and an excited state. The way this pans out in this type of formalism would be two sets of equations for particles A in the ground state and equations for particle B in the excited state with some energy flow terms between those two types of particles. You could imagine adding things like viscosity to this kind of formalism. There's many things that can be done.
May I ask you something? Otherwise, I lost you completely. So in this equation, you have only one row. Okay, so one.
It's row of R and.
So are you tracking the host and the?
This is for a spherical symmetric object.
But you have two, no? You have the host and you have the.
So you imagine, you need some kind of prescription.
So where is the projectile?
So you don't actually map the projectile in here. You calculate some evaporation rate. You take that to be some function of time, let's say. You don't really take into account the fact that there is no spherical symmetry anymore, because it doesn't really matter, because as soon as two particles interact with each other, most of the time, the end result is that both of those particles just get emitted from the system. So the fact that you lost symmetry doesn't really matter. And so you don't actually model those projectiles. You just model the evaporation rate as being some rate that is a function of time, let's say.
So rho is the density of the projectile or the...
Rho is the density of the halo that you're modeling a single halo here. Let's say it's a sub-halo of some object orbiting the Milky Way. It's a spherical symmetric system. You're modeling rho as a function of r and t. That's what you're solving for. And if you add evaporation, you're adding some rate of mass removal of particles for whatever reason. Secretly, you know that it's happening because of evaporation, but it doesn't matter.
I see. Okay.
Cool. Okay, so let me just show you how this formalism can be used to, actually place bounds or search for signals of a specific example of self-interacting dark matter. I'm not going to talk about this too much because Manoj is going to give a whole talk about self-interacting dark matter later. But for this model that I'm considering here with a scalar mediator, you get a Yukawa potential type interaction between your particles, and the cross-section is constant at small incoming particle velocities, and it looks like that form. And then as you get to velocities that are larger than the ratio of mediator to dark matter mass, you get into the Rutherford regime, and your cross-section starts to fall off like v to the minus 4. Okay, and so the actual parameters that you ever have a chance of constraining or being sensitive to are this cross-section at zero velocity and this ratio of mediator to dark matter mass. So what we were able to do in a paper that came out about 4 years ago is we were able to take objects like Draco, one of the classical satellites of the Milky Way, and ask which region in this parameter space is inconsistent with measurements of the velocity dispersion of stars in Draco. So you take the velocity dispersion of stars in Draco. That tells you something about how much mass is enclosed in the half-light radius of Draco. And in this blue region of the parameter space, objects core too much to be consistent with that measurement. And that's true even marginalizing over concentration and mass of the subhalo that Draco lives inside. And so on the left-hand side here, the cross-section is small enough such that you don't really do anything to your subhalo. In this region of the parameter space, you're going to overcore too much to be consistent with the central measurement. And in the region to the right, cross-section is large enough such that you gravithermally core collapse, and you're able to reconstruct the central density of Draco to within 2 sigma. And so just to say that same thing in another language, if there's like a bullet cluster bound at around 1,000 kilometers per second that tells us that the cross-section there needs to be below around 1 centimeter squared per gram, what we find is that for dwarfs such as Draco and a bunch of others that we looked at, you need either very small cross-sections or very large cross-sections at these small velocities. So that turns out to be what seems to be consistent with the data. And so let's ask, how can we probe this region to the right with a similar formalism that I've set up here? So let's look at two cross-sections, some cross-section with a smaller value of this omega parameter and a cross-section with a larger value of this omega parameter, and ask what is the time scale for core collapse for each of these. So this is a kind of a complicated plots, but just to walk you through them, the left-hand side is this smaller cross-section value. The right-hand side is a larger cross-section value. In each of these, the x-axis is the virial mass of subhalos, the y-axis is the concentration of those halos, and the thickest red curve in each of these is the curve above which gravithermal collapse happens within the age of the universe. Okay? So and the gray in each of these is the standard CDM mass concentration relation. Let's take a slice in each of these plots at 10 to the 10. So 10 to the 10 solar mass objects with this small cross-section in the entire range of mass concentration relation have not had enough time to core collapse. In the right-hand plot for the larger cross-section, 10 to the 10 solar mass objects fall into two categories. The category that started their life off with lower concentrations and have not had enough time to collapse, and the category with high concentrations that have had enough time to collapse. And so you can imagine now turning this into a probability distribution of what you expect in terms of mass enclosed within the half-light radius of objects. Okay, so look at these two panels. These are low cross-section, high cross-section. And you see here in the high cross-section, this is half-light radius as a function of half-light mass. And you see a PDF of what you expect. And you see this dichotomy. These are the objects that have had enough time to collapse. These are the objects that have not had enough time to collapse. And overlaid on top of this are the ultra-faint dwarfs of the Milky Way. And for the lower cross-section, the prediction is that for this cross-section, everything is in the core expansion phase. And so you have a prediction of lower mass at small half-light radius, which seems to be inconsistent with the data here. Okay? Very good. So you can see how the simple kind of formalism can be used to make predictions that can then be compared to data. And this, for example, might be a cross-section that is ruled out. Any questions about this? Okay, so I only have 2 minutes left. I'm just going to very quickly introduce semi-analytical models, and then I'm going to leave the rest of that for the discussion session. But this idea of semi-analytical models, and I'm going to introduce a famous model called SatGen by an author called Fangzhou Jiang from 2020. And this is a model that is essentially a way of creating large statistical ensembles of satellite galaxies, including many of their properties. Sorry, this is also by Frank. And the idea here is that what you do is you take a merger tree and you take all of the statistical properties of that merger tree, and you have your satellites merging where children merge into a parent that merges into a parent. And for each of these objects, you get to track the density profile as a function of time, including things like tidal stripping and tidal tracks and the effects of baryonic feedback and so forth. And what you get at the end of the day is a large ensemble of objects, who they belong to, and what their density profiles look like as a function of time, including both dark matter and baryons if you want. And you're able to easily vary over all of the statistics and all of the systematics of these systems, and also get the orbits of the object inside of their parents. So you very rapidly get huge ensembles of statistics that you maybe care about, whereas running a full simulation of this might just be an overkill. And this was mentioned in Adrian's talk. This is a paper that came out a few months ago that Duncan led from Stony Brook and also Aditya. And what Duncan did in this paper is he took SatGen, just for the case of CDM, and ran it, including a GD1-like stream running real-time inside SatGen. And he was able to take objects. So this is an example of a specific encounter of a GD1-like stream with a CDM subhalo that's close enough to create an effect. and calculate the impulse curve along that stream and ask what is the probability that this event creates a gap that might look like what is observed in GD1. And then for each of those events, he ran an actual simulation of that event, including star particles. And this is an example of an event that ended up looking as if it has a sizable gap in it. And then he was able to do this statistically for many, many Milky Ways and many, many encounters, and plot, correlations between things like the subhalo mass at infall, the subhalo mass at the time of the event, and also calculate the predicted number of gaps in Milky Way-like systems. Okay, and so you can imagine taking this, now plugging in SIDM or SIDM with dissipation, and doing the same kind of thing and asking, which region of the parameter space predict 10 gaps in GD1 or 0 gaps in GD1. And so basically, I'm going to end with this. The idea would be, take a kinetic theory of whatever it is that you care about, build intuition, take that now, plug it into a SatGen-like emulator, and then run for whatever it is that's your observable, and try and make predictions. Find the region of parameter space that you don't care about because it's ruled out. Find the region you do care about, simulate that, and then compare to data. And basically, this slide says what I just said, so I'm going to end with that.
Awesome, thanks, Oren. We have time just for a few questions. Ani?
Can I ask about the kinetic theory? Well, presumably when you do this, you have to have some prior on the distribution function in order to calculate those averages to get the moments.
You're talking about the probability distribution?
Going from from Boltzmann equation to fluid equations, you need to have some. Are you averaging over like a Maxwellian or something with some temperature?
I mean, you have initial conditions, and you set them, and then you. I mean, the equations are fully consistent. I don't know what you mean by a prior. There's no sense in which there's anything statistical in that calculation.
Well, you average when you calculate moments. You have to average over. What are you averaging over? I guess.
What am I averaging over? You're asking about the velocity distribution?
Yeah, the velocity distribution. Because, I mean, this is assuming, I guess, you have some equilibrium. So do you lose, like, when you reduce to fluid equations, do you lose information about, say, non-equilibrium physics?
You lose information about physics that is beyond the moments that you're calculating, but you get the non-equilibrium effects. So I'm not 100% sure about your question. Okay. Maybe we'll talk about it afterwards. Okay. I think I might be...
It could be just semantics that I'm asking about.
Maybe I'm missing something about the question.
Yeah, I want to ask, given the uncertainties we've heard about stellar streams, etc., what constitutes a detection in these scenarios? Like, how would you tell that this is SIDM and not unknown standard model physics?
I mean, that's something that I was going to bring up in the discussion session. My feeling from learning about streams is that it's not going to be very easy to make a detection. It's going to be easy to maybe rule out things. I don't know, maybe Adrian can comment on this. But because there's a lot of backgrounds that are not very well understood, I think even if we saw, if there was some prediction from SIDM and then we kind of saw that, it would be very difficult to say, oh, this is SIDM. But if there was a prediction that we didn't see, and that prediction, was like a large effect, we could rule things out. So I think it's going to be very difficult to actually rule things in. Detect.
Maybe one more question, and then we'll go to a break. Frank.
All right, great talk. So one thing that you didn't mention, and so in this work, like what is shown here, what is this based on is calculating collapse times for core formation, core collapse, and that is sort of taken by saying, okay, given a system, how long does it take? But during that time, the system typically evolves. And a particular one that I think is hard to take into account, and I haven't seen any work that does a good job in that, at least theoretical, is the fact that these things, until they're subhalos, are actually still accreting mass. So they're growing a mass. So it's the opposite of the...
You're right.
Things.
I mean,
and
that's something...
That could significantly delay the core collapse compared to the calculations that you're doing.
I think that's true, and it could, in principle, be added to the equations, right? I guess if you wanted to actually turn this into a real bound, you'd have to think whether that makes, makes your result more conservative or less conservative. And if it becomes an issue, then you just wouldn't be able to say very much unless you model it correctly. Yeah, I totally agree. I mean, there's many things that haven't been taken into account here, and that's one of them.